going to see a proof of Levy's monotone convergence theorem for upper functions. We have already proved the theorem for step functions. In this video, we will adapt the argument given there to the general case of upper functions. In the next video, we will break up a Lebesgue integrable function as a difference of two upper functions and get a Levy monotone convergence theorem for all Lebesgue integrable functions. So here is the statement of the theorem. It's exactly similar to what we have seen for step functions. Let Fn from I to R be a sequence of upper functions such that number 1, Fn increases almost everywhere on I. Note there is a slight difference in this version compared to what we saw in the last video. There we assume that the step functions are increasing everywhere. That's simply because step functions take only finitely many values. Think about why assuming almost everywhere for step functions makes no sense. Second, limit n going to infinity integral over I Fn exists. So the integrals are bounded above in essence. Then Fn converges almost everywhere to a function f, which is an upper function, and the integral of f is nothing but the limit of n going to infinity integral of I Fn. So in some sense, you can interchange the limit and the integral. The limit and the integral can be interchanged. One nice aspect about the monotone convergence theorem is that we are just assuming that the limit n going to infinity integral of I Fn exists. That automatically guarantees the existence of a limit function f whose integral is exactly the limit of the integrals, which is something nice. Okay, so as I said, we are going to use the fact that we have already shown for step functions. So proof, by definition we can find an increasing sequence of step functions S and K that generate Fk. Recall, this means that S and K increases almost everywhere to Fk. Here n is the index, so I should write almost everywhere, and this integral S and K over I, this limit n going to infinity exists. This is the meaning of S and K's generate Fk. So let's arrange them all in an array. We have S11, S12, S13, ... and this increases almost everywhere to F1. Similarly, we have the second one, S12, I made a slight mistake in the indexing. The running index is n, not k. So let me just fix that. So you have S11, you have S21 ... converging to F1, then you have S12, S22 ... converging to F2. You have this in both directions. Okay, and note these S and K's are increasing sequence of step functions. They are an increasing sequence of step functions and they increase almost everywhere to Fk. Okay, now what we are going to do is we are going to produce new step functions combining together the data obtained by these step functions which converge to Fk, right? So what we do is we define Tn of x by definition to be max of Sn1 of x, Sn2 of x, comma ... Sn of x, right? So what are we doing? We are looking at the nth column, we are looking at the nth column, and we are taking the max all the way up till the nth entry. Okay, so we start at, for instance, T11 would be just S11. T1 would be just S11. T2 would be the maximum of S21 and S22. Okay, and T3 will be the maximum of S31, S32, S33, all the way up till the third entry. Okay, now because we are taking the maximum always to the right, that is Tn plus 1 will be obtained by taking a maximum of functions which are to the right of the functions that you're taking for Tn, and since each row the functions are increasing, it's straightforward to see that Tn plus 1 of x is greater than or equal to Tn of x. That is, Tn is an increasing sequence. Furthermore, since it's a maximum of finitely many step functions, it is also a step function. It's an increasing sequence of step functions. Excellent. Now, by definition, we have Snk of x is less than or equal to Fk of x almost everywhere. Okay, because the sequence S and K's generate the function Fk, and since Fk's are increasing almost everywhere on I, well, we automatically have that Tn of x is going to be less than the maximum of f1 of x comma f2 of x dot 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 fn of x, right? Now, of course, this will be true almost everywhere. And notice that because these functions f1, f2 dot 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 fn's are also increasing almost everywhere, I can write this is less than or equal to fn of x almost everywhere. So the net upshot is Tn of x is less than or equal to fn of x almost everywhere on I. Okay. Now both sides are upper functions, so we can use the results involving upper functions and the behavior of integrals under order to conclude that integral over I Tn is less than or equal to integral over I Fn. But our hypothesis is that limit n going to infinity, integral of I Fn exists. And since this sequence of integrals is an increasing sequence, this means this quantity integral I Fn is bounded above, which means that integral of I Tn is bounded above, and since these Tn's are increasing functions, the net conclusion is that Tn's must converge to a function g in U of I. And this follows from monotone convergence theorem for step functions. Okay, so we have just constructed these new step functions which are increasing, and because these new step functions are increasing and they are bounded above, we get that we get a limit function, and not only that, we get that integral of g over I is nothing but limit n going to infinity integral over I of Tn. Okay, now what do we do now? We are going to show goal is to show that Fn converges to f almost everywhere, and integral of I f is nothing but limit of n going to infinity integral of I Fn. Let's keep this goal in mind. Okay. Now, as we have observed before, Snk of x is less than or equal to Tn of x if k is less than or equal to n. This is because we are just taking the maximum of Sn1, Sn2 dot 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 Snn. So this is just by definition. Okay. Now take n going to infinity. Take n going to infinity. So what you will get is fk of x is less than or equal to limit n going to infinity Tn of x, which is just f of x, but this will be true only almost everywhere. This will be true only almost everywhere. This means that the increasing sequence, that is, it's almost everywhere increasing, of course, fk is almost everywhere bounded above by f. This means fk converges almost everywhere to some function g from I to R. Okay, but we already know that by our construction these functions t and x are less than or equal to f and x. Recall, these t and x's were obtained by taking the maximum along the nth column all the way up till the n, and since the functions here to the right are all almost everywhere greater than or equal to, we get this inequality that Tn of x is less than or equal to Fn of x almost everywhere. Okay, now letting n go to infinity, we get that the limit of the left hand side is f of x by definition, and the limit of the right hand side is g of x, and this is true almost everywhere. Okay, but we also have g of x is less than or equal to f of x almost everywhere. Why do we have g of x is less than or equal to f of x almost everywhere? Well, we already know that fk of x is less than or equal to f of x, and this is just the pointwise limit of fk of x. Therefore g of x will be less than or equal to f of x. Combining both, we get f of x equal to g of x almost everywhere. Excellent. Now we have to show, what remains to be shown is integral of if is limit n going to infinity integral of I fn. Okay, we have the following relationship that we have obtained earlier. Integral of I Tn is less than or equal to integral of I Fn, and taking limits will tell you that integral of if is less than or equal to limit n going to infinity integral of I Fn. We also have the relationship that fk of x is also less than or equal to fx almost everywhere on I. Okay, and again that means that integral of I fk of x is less than or equal to integral of I f of x, and taking limits on both sides tells you that limit n going to infinity of integral of I fk of x, or rather limit fn of x, is less than or equal to integral of I f of x, and we are done. So this concludes the proof of Levy's monotone convergence theorem for upper functions. In the next video, we shall use this result to show the similar result for Lebesgue integrable functions. This is a course on real analysis, and you've just watched the video on Levy monotone convergence theorem for upper functions.